My career began when I had a Vietnam commitment after I graduated from engineering school at the University of Cincinnati. And I unfortunately scored very high on all of the military exams, and they wanted me to be a second lieutenant officer in Vietnam. I thought I'd rather do something else, and I was put into what I call the Critical Skills Corps as a civilian, and was deferred from active military duty to developing aviation control systems for aircraft. And while I was working in the aircraft industry for Ling Tim Quo Vought, I designed a device for controlling blood pressure. And I went to the medical school, had an appointment with the head of physiology, and in fact then learned that my device would not work. But that led to me being admitted to the medical school, where I completed my education in physiology and worked in the surgical, became a assistant professor in surgery and physiology at Southwestern Medical School. And there I became fascinated with heart failure research, and probably dealt with over 200 heart failure patients. And that led then to my involvement with assisted circulation and the intra-aortic balloon, and I combined that with other adjuvant agents to increase the blood flow of the endocardium in heart failure animals. And eventually then we went on to the same work in human patients, and that led to my appointment to the NIH. I've had 10 years working in private industry, in the power industry for the Indianapolis Power and Light, with National Cash Register for business and electronic machines, in the aircraft industry. I worked on 3 military aircraft. I had some wonderful engineering problems to solve. And then I went on to NIH, where I worked 27 years in the public sector, and I've had 20 years working in academia. So I've had time in all 3 sectors. The interesting thing is that the least efficient part of that is in the academic sector, and very diffuse leadership in that area. The most comprehensive and direct was at NIH, where you could follow a certain path and accomplish a certain goal. Yes, it was an exciting time, and still is an exciting time. I think the opportunities for young people are enormous. In our time, it was a bit of a stretch for people to accept that aerospace engineers or mechanical engineers, electrical engineers could provide benefit to the medical research process and develop technologies that were useful for both diagnosis and treatment of medical conditions. I was fortunate in that within the National Heart, Lung, and Blood Institute, they had a grasp of the value of engineering, particularly for heart disease conditions and disorders. And I was actually asked shortly after joining the NIH to develop a program for imaging less invasively coronary artery disease. And that program led to both the spatial the quantitative and the characterization of coronary artery disease through MRI imaging, ultrafast CT, improved ultrasound. We had subtraction angiography. It was a wonderful time in terms of developing these imaging systems, which of course are the basis of modern medicine today. So those were used for the diagnosis of heart failure and for obstructive coronary disease. And then we were also asked to create the first totally implantable artificial heart, and that work led to the use of various types of assist systems and replacement systems for cardiac heart function, including the materials that were used. So we also had responsibility for developing the biomaterials programs of the NIH for cardiovascular disease, and that pathway was guided by Pierre when he headed up that biomaterials task force in 1977. That was interesting, and the result of that was a series of programs. We created the two guidelines. One was the guidelines for the physical characterization of biomaterials. The other was the for the in vitro and in vivo evaluation of biomaterials, two separate sets of guidelines, and also the primary reference materials. There was a need for developing primary and secondary standards so that results between laboratories could be compared, and it provided some quality assurance for the field. Probably the most important thing that came out of that was the RFA on blood material interactions. That started the field of grant-related research beyond the artificial heart contract research programs. We also had special fabrication programs where we learned to do things that are now quite simple with 3D printing, but at the time three-dimensional fabrication was a new field, and so we had some exploratory work in that and provided the same quality of fabrication for all of the various research teams so that they could move ahead together with the same quality of materials and fabricated systems. Even the test systems were provided by the NIH to the various laboratories. We have patients that have been on assist devices for 10 years, and the number of cycles, since these are now rotary systems, continuous flow systems, they do the equivalent of 40 billion cycles. Few man-made or woman-made systems have ever functioned for 40 billion cycles, and they're still running and look like they'll run indefinitely. So it far exceeds any military specs, and that all came out of the reliability programs and quality assurance programs. The support for bioengineering research report demonstrated that the amount of funding going into basic bioengineering research was about half of that in the other areas that NIH supports. In other words, almost all of the disciplines at NIH are supported about 60% in basic research, which is the major objective mission of the NIH. But in the bioengineering discipline, it was 30%, roughly half. And it's important that the support for basic bioengineering see growth towards that of all the other disciplines, with 60% for basic research and 40% for translational and applied research. One of the things that is also benefited the medical and biological engineering field is the Small Business Innovation Research Program, which dovetails nicely with the goals of, say, a medical device innovation, where that can help move a startup in that field towards the long road that leads to commercialization. There are roughly 10,000 medical device companies. The FDA regulates around 250,000 medical devices. And it's quite an interesting field, with 75% of the companies have 75 or fewer employees. So a number of them are, basically one product line that is managed quite effectively by a relatively small company. And their patenting position, their reimbursement, their regulatory requirements, their quality assurance, it's quite remarkable, actually. The access to new medical device innovations, drug and biologic innovations have moved overseas, and most first in man or woman is done overseas rather than here in the United States. And it would be nice to reverse that situation. The deleterious effects are particularly with education. If you have a research center and it's located overseas, then the universities nearby that research center bring in talent that will supplement that of the private sector research center. So not only do we lose the jobs and the research center to another location, we also lose talent that's brought in to the research universities nearby to that research center. And we're not gaining that talent in our research universities. And so the accessibility and the loss of talent and the loss of ideas and everything, Congress, administrations need to begin to provide incentives for bringing that back on shore. Of course, there are easy ones through tax systems, through looking at more post-market surveillance rather than pre-market evaluation. And there's integrative approaches to that could be taken, and that's an important area for AIMBE to be in the forefront of providing, again, a leadership in single areas where they can have an impact, and if they can work within existing policy to do that, and then if new policy is needed, to have the perseverance to see it through. That's the major attribute. When good ideas, money follows good ideas, but having the persistence to keep that good idea in the forefront is a critical element.